This is Fundamental Problem 9 from Chapter 14. If the motor winds in the cable with a constant speed of 3 feet per second, determine the power supplied to the motor. The load weighs 100 pounds and the efficiency of the motor is 0.8. Neglect the mass of the pulleys. So the power supplied to the motor, that is the power input, which I'll call Pn. So that's what we're looking for. We have the efficiency, so the power that we find here is going to be P out, and then we use equation 1411 to find P in. They tell us to neglect the mass of the pulleys, and I talked about this in a previous video, but just to summarize, if we look at pulley B, and let's call this rope 1 and this rope 2. So rope 1 exerts a force upward on this side of the pulley and on this side of the pulley, so that's T1 on the left and T1 on the right. And rope 2 exerts a force downward, so that's T2. Using Newton's second law in the vertical direction, with the mass being equal to 0, the sum of the forces acting on pulley B must be equal to 0 because the mass of the pulley we're neglecting, so we can say it's equal to 0. Now in this case, actually, you don't have to use that. You don't have to assume that the mass is 0 because we're going at a constant speed. And so the sum of the forces, you could say, is equal to 0 because the acceleration is equal to 0, in which case you don't need to say that the mass is equal to 0 in order to have the sum of the forces acting on the pulley equal to 0. But if we are able to neglect the mass of the pulleys, then even if the acceleration is non-zero, you can set the sum of the forces acting on the pulley equal to 0. Now, also, which they didn't mention in this problem, but we're going to treat the cables as being massless also, and if you treat the cables as having no mass, then any point on the cable will have the same value for the tension, which is why we can say this is T1 and this is also T1, so those forces have the same magnitude. And not only that, but when you look at the free body diagram for box A, you have the force of gravity acting downwards, which is 100 pounds, and you have the same tension that you had here acting upward because it's the same cable. So now that I have my free body diagrams, let's go back and look at what I want to calculate here. So I want to find the power supplied to the motor, and I know the efficiency is equal to P out divided by P in. So I want to find P out for the motor, which will be the force here, which the motor exerts on the cable, which is T2. So that's T2 dotted with V. I know the velocity is 3 feet per second, and I don't know what T2 is, but I can pretty easily find T2 from looking at my free body diagrams here and noting that in this case the acceleration is equal to 0, so the sum of the forces for load A is also equal to 0, therefore T1 is equal to 100 pounds, and looking at the free body diagram for pulley B, we can say 2 times T1 is equal to T2, therefore T2 is equal to 200 pounds. And then we have the velocity here acting downwards, so when I do the dot product here, the tension and the velocity are acting in the same direction. So I have T2, which is 200 pounds, times my velocity of 3 feet per second, and that gives me 600 foot-pounds per second, but I don't get to leave the answer as 600 foot-pounds per second. I have to convert it to horsepower. So you should either have it written on your equation sheet, or perhaps have memorized, or you get to look it up in the textbook, that 1 horsepower is equal to 550 foot-pounds per second. So to convert this to horsepower, we multiply by 1 horsepower divided by 550 foot-pounds per second, and that gives us 1.09 horsepower, but this is not the answer because this is the power output from the motor and we want the power input, so we use this equation here, and to find P in, we have P out divided by the efficiency. So that's 1.09 horsepower divided by the efficiency, which they told us was 0.8. Therefore, we get 1.36 horsepower for the power supplied to the motor.